let's get going. So it's a pleasure this week to have Tommaso Treu from University of California in Los Angeles, UCLA. Tommaso, as you might guess from his name, is Italian, and he did his PhD in Italy at the Scuola Normale Superiore. I don't know how my pronunciation is. And then he went to Caltech, where he was a postdoc, and he was a Hubble Fellow at UCLA. And subsequently, he was at Santa Barbara and then moved to UCLA, where he is now, and he's been for many years. He's won a number of awards, including the Newton Lacey Pierce Prize from the AAS. He's most known, I think, for what he's going to talk about today from a broad perspective, which is strong gravitational lensing and its application to a bunch of problems in the universe, so which I'll maybe mention a few of them today. Broadly speaking, things like the structure of elliptical galaxies and also cosmological parameters from strong lensing. So without further ado, take it away, Tommaso.
Thank you, Mike. It's a real pleasure. Thank you for giving me this opportunity. So what I would like to talk about is really perhaps the question that has been motivating my entire career ever since I decided to be an astrophysicist at the age of 6. It's like, what's the universe made of? I really wanted to know what makes up reality. And this is a very, very, I think, fundamental question that humans have been asking since the beginning of time, and one that we quite don't have an answer for. In fact, 95% of the universe is made of something that we don't have a clue about its nature. And so, as I will show you, strong gravitational lensing is a tool that is very powerful in understanding the nature of this dark component of the universe, because the only thing we know about the dark component of the universe is that it interacts gravitationally. And so being able to study the dark universe using gravity alone has a tremendous power. And I will show you 2 examples of this. So this is a brief outline of my talk. So first I will give a very brief introduction. I don't think I need to spend much time with this audience, but the view from Earth and the view from space, and how can we try to reconcile them. And then there's traditionally 2 ways to learn about the dark universe. One is to study the expansion history of the universe, because the content of the universe drives its expansion. And in the past few years, a problem has emerged known as the Hubble tension. And I will describe how we can use gravitational lensing to learn about the expansion history of the universe, and the Hubble tension in particular. And then there's an issue about the nature of dark matter. Most people probably accept that dark matter is cold, some sort of massive 100 GeV scale particle, but there's really a whole zoo of particles and theories about what dark matter could be. And I will describe how a technique called flux ratio anomalies provides possibly the best constraints on the nature of dark matter to date. And for each of the 2 topics, I'll give a brief outlook at the end. And feel free to interrupt me at any time if you have questions. So if you ask a physicist, they will say that in an accelerator, you slam together particles at very high energy, and those collisions are very well described by the standard model of particle physics, where you have quarks, force carriers, and leptons. And that's great. That's really a triumph of physics, I would say. The thing is that, if you try to explain the universe with the same ingredients, you fail. There's no way we would have the universe that we see today if we only had the standard model of particle physics. And so the current description that we have, it's quite bizarre, and it postulates that 95% of the mass energy content of the universe is made of something that we call dark matter. It's some sort of mass, non-relativistic mass that doesn't seem to have any interaction other than gravity, and dark energy, which is something with a negative pressure that makes the universe accelerate. Now, we measure these 2 things quite precisely in terms of their abundance, but we really don't know what they are. And so this is what this talk is all about understanding what they are. So let's start from the expansion history of the universe. We know the content of the universe drives the expansion history of the universe through Friedmann's equation. So being able to reconstruct the expansion history of the universe is one of the main ways in which we learn about the content of the universe. And as of the past 2 or 3 years, an interesting tension has emerged between measurements of the Hubble constant obtained from late universe probes, like, for example, the local distance ladder, and early universe probes. You can imagine using Big Bang nucleosynthesis or the cosmic microwave background fluctuations within the context of some cosmological model to extrapolate the value of the Hubble constant to present time. And this is a plot that is already out of date. Much has happened in this field since when we put this together a year and a half ago, but it kind of like summarizes the situation. There's a tendency for late universe probes to yield larger values than early universe probes. Now, if this is true, of course, it has profound implications because the comparison is carried out under the assumption that the standard model of lambda called dark matter, a model where dark matter is cold and dark energy is just a cosmological constant, is the correct model. And so if this, and they should yield the same measurement of the Hubble constant. If they don't, and these measurements are correct, then in order to explain, you have to introduce some kind of like exotic ideas. So some early dark energy or some early particle that changes the sound horizon at recombination. But it's really not easy, and there's no natural way to do it. As you know, you can debate about the meaning of the word natural when we're talking about dark energy and dark matter. But so explaining this away with theory is pretty difficult. And there's, of course, the possibility that some of these measurements may be wrong. And although statistically the tension is fairly significant, it's important to obtain multiple independent measurements to investigate unknown unknowns. And so here is where time delay cosmography comes in. So time delay cosmography is based on gravitational lensing. And here I want to show you a brief example of gravitational lensing in case you're not familiar with it. So this is a picture of a cosmic string. These are topological defects left over from an inflationary era. And there's do you see my cursor? And this is a distant quasar. And due to peculiar velocity, the distant quasar gets close to the cosmic string, and you form another image of the distant quasar. And so this is a phenomenon known as strong lensing. It turns out that the edges of a water tank are pretty much the same optical properties as cosmic strings. And one thing you may have noticed here, if you have picosecond resolution, is that the second image of the fish happened a little later than the first image, because the photons had to go, in this case, through a piece of glass where their speed is reduced and follow a longer path. But in general, this happens every time you have a high density of matter along the other side. And the best analogy for a galaxy, for example, is the stem of a wine glass. It gives you the same optical properties. And as in the case of normal optics, you can use gravitational lensing to infer the properties of the deflector or to infer the properties of the trajectory of light along the line of sight. And so how does it work in this case? So there's an observer, us, and there's a source. And the source is varying with time. So it's variable like a quasar or a supernova. And two rays reach us thanks to the deflection by a foreground lens galaxy or quasar. And ray A goes to the shortest path and gets to us first, and ray B gets to us later. Now, it is a simple geometry problem to convert this red stick, of which we know the length, because it's just delta t times the speed of light, into all the other distances. And measuring distances is one of the main ways in which we characterize the expansion history of the universe, because being able to measure how distance changes with time is perhaps the primary way in which we measure the expansion history of the universe. And so in practice, you measure the distance in arrival time, difference in arrival time between two images. This is proportional to a distance that we call the time delay distance, which is a ratio of angular diameter distances, which in turn is inversely proportional to the Hubble constant like every distance. And it depends on other cosmological parameters like the matter density of the universe, the equation of state of dark energy. And so the steps are measuring the time delay between the two images, measure and model the potential. So we need to know how the deflection happens, infer the time delay distance, and from that infer cosmological parameters. So this is not a new method. It's something that was proposed in 1964 by Refstel, and it actually was proposed well before the first strong gravitational lens was discovered. They were only discovered more than 10 years later at the end of the 70s. So people got very excited, and in the 80s, they started to measure these time delays, and they couldn't quite agree. And it turned out that there were challenges in measuring these time delays because it requires pretty high cadence, and it requires being aware of something, a phenomenon called microlensing. So by the end of the 80s, they sort of figured it out mostly. And so in the 90s, they tried to apply this to measure the Hubble constant, and they got pretty strange results. And here, the issue was that due to the poor quality of the data available at that time, they had to use oversimplified mass models. And so the error budget was not correct. So finally, about 20 years ago, things came together due to a number of technological and methodological improvements. So we were able to improve monitoring techniques with higher cadence and precision. We understood that we needed observables that were not lensing related, like stellar kinematics, that helps us to break some of the degeneracies in lensing. And with Hubble, we were able to observe not only the point sources in the multiple images, but also the extended sources. So for a quasar, you can also observe the host galaxy being lensed. And by about 2010, we were able to put it all together and show that we can make a 6 to 7% precision measurement of a single distance from a single source. And at the 50th anniversary of Refstel's method that they proposed to use as lens supernova, we finally discovered a lens supernova, and that was quite exciting. And I will show you a little bit of that, but stay tuned because we are about to reveal a new measurement of the Hubble constant based on supernova Refstel. And I will not be able to tell you about this today because it's still embargoed, but it should be out pretty soon. So, okay, this is great in theory, but in theory, there's no difference between theory and practice. In practice, there is. So how does it work? Well, this is supernova Refstel that we discovered in 2014. You can see this is an image taken in February of this galaxy here in this quadrant, and you can see there's nothing around it. And then in November 2014, we see 4 images appear. These are 4 images of a supernova that explode in this host galaxy redshift 1.5 that was lensed by this galaxy in this cluster. The interesting thing of this case here is that we knew that another image of this supernova, if our understanding of general relativity is correct, we knew that another image of the supernova should appear about a year later. So we put together a large effort and we asked many modelers to predict when the new image should appear. And they all said towards the end of 2015, the beginning of 2016. And this was a true blind prediction because at that time, the target was not observable by Hubble. So we had no idea if the supernova had already appeared or not. When we took the images, finally, it was like deja vu all over again. So the image was not there in April 2015. And in December 2015, exactly as predicted, it appeared where it was predicted to appear. So this should give you some confidence that we know what we're doing, that the general relativity works because you can predict where new images should appear. And also that our modeling techniques are kind of like good enough to make this kind of measurements. And so this is, you can read all of this in a paper, and soon this will be superseded by a couple of papers that we're finishing up and should be on archive soon. And this will be a new measurement of H0 based on supernova Refstel. Okay, so this is a proof of concept, but most of the work that we'll be presenting today is based on lensed quasars. So in the case of lensed quasars, you have to solve 4 problems. First, you have to measure the time delays, and this can be done by monitoring at high cadence and high photometric precision. You have to have very accurate astrometry. You need to know the position of these images to about 10 or 20 milliarc seconds. And that can be done with Hubble, with a very large array, and in some cases with adaptive optics. Then we need to model the lensing potential, and we do that through stellar kinematics and extended sources. And then the fourth ingredient is that you also need to know what happens along the line of sight, because photons don't really travel in empty space. They travel through large-scale structure. And so the trajectory of a photon is really a lot of little deflections until it hits the main deflector and gets a big hit. And so we need to put it all together, and we did. And you can see here how the data quality has improved. This was like a typical 80s light curve, and this is a typical 2000 light curve. And you can see even by eye here in 2008 that this wiggle, this image here is delayed by with respect to the three images by about 100 days. So you can get like percent-like precision measurement of the delay. Here, you can see how the data improved in terms of, this is what was available in the 90s. People had barely images of the four, could just see the images of the point source, the quasar. And nowadays we can see not just the images of the point source, but also multiple images of the host galaxy. And that gives us information about the potential on the entire image. And this is data, and this is model to tell you how well we can do this kind of reconstruction. And then we decided that, we figured out we could use stellar kinematics to further improve our mass models. And whereas until the 2000s, this was ignored, the effect of the line of sight, we figured out a way to statistically treat that by looking at cosmological numerical simulations and picking out line of sights that look like the line of sight we're looking at, and statistically determine if the line of sight is producing an excess of convergence, an excess of mass, sort of focusing the light, or an excess of defocusing. And that can be treated statistically. Right. So another thing we did is since this is a very difficult measurement, we did all of this blindly. So all our measurements are blinded in the sense that we carry out the measurement, we freeze everything, we write the paper, and we only figure out what the Hubble constant is at the last minute. And we don't change that number. We just publish the number that comes out of the analysis without changing that. And that is important to prevent experimental bias. And so this was the result that we got about a year ago, combining SHOES, which is the Adam Rees team of Cepheid-based determination of Hubble constant, with 7 lenses. And the tension is fairly significant from a statistical point of view. There was a difference of more than 5 sigma between the 8 late and early universe probes. Now, at this point, you're facing an interesting choice. You can decide, well, one of the two things is possible. Either lambda CDM is wrong, or your measurement, in some sense, is not right. And so either one of the assumptions in lambda CDM is wrong, or one in the assumption that goes into your measurement is wrong. So since rejecting lambda CDM is a pretty big deal, we decided to go and revisit all of our assumptions and see if we can drop some of the assumptions and perhaps obtain a different result, and see, because if it's really a true problem in the cosmology, it should withstand this kind of test. And so we've been revisiting assumptions in the past year. And one of them is perhaps the most important, and I will tell you about this in a second. So in our analysis, we have assumed that the mass profile of elliptical galaxies can be well described either by a power law, where the total density of mass is a power law, r to the minus some number, that is a free parameter, or stars with some mass to light ratio that converts the observed surface brightness into mass, and some sort of Navarro-Franken-White dark matter density profile. These are pretty standard assumptions that well describe the mass density profile of elliptical galaxies. And if you read the literature, there's decades of work that support this kind of assumption. So these are not far-fetched assumptions in any way. They're very reasonable. Here are 2 quotes, one from X-ray measurements and one from stellar kinematics, that show that this is a good description of the data. And also in theory, that's kind of like what you expect from numerical simulations. But so first we checked, okay, is there a difference between the 2 mass profile assumption, power law and stars per NS7 FW, that we call the composite? No, they give exactly the same measurement of H0. So what can we do? So we're studying this in more detail. And these are mass decompositions of elliptical galaxies where you show the stellar mass, the dark matter mass in gray, the stellar mass in blue, and the total in purple. The total mass density profile is always very well described by a power law, but there could be very small deviations at the level of a few percent. And maybe these very small deviations could potentially affect our determination of the Hubble constant. So we took a radical approach and we developed the following decision tree. And since it is given the importance of this measurement, let's try to follow a completely different approach. So this is what we've done in the past, describing galaxies with standard mass density profile, and you end up with this measurement of H0. Or you can say, let's make no assumption whatsoever on the radial mass density profile of the lens galaxy. And for those of you who are lensing aficionados, this means in practice implementing the mass sheet degeneracy in a way that drops every lensing constraint. So at this point, the mass density profile of the main deflector is only constrained by stellar kinematics. Once you are using stellar kinematics as constraint, you are prone to what is called the mass anisotropy degeneracy, because once you try to invert kinematics obtained along the line of sight into a three-dimensional problem, you have to worry about what is the true three-dimensional distribution of velocities in the phase space of the galaxy. And so at that point, you have another branch in the decision tree, and you can say, how would I be able to learn about the properties of these deflectors in a way that it's not lensing related? And you can make the assumption that all elliptical galaxies are similar, which is a reasonable assumption, but we don't know if it's true to this level of precision, and assume that there's another sample of lenses called slacks, that they are a lower redshift, or we can assume that they are very similar to the ones that we use for the time delay cosmology measurement. And so if we just use those to infer the stellar anisotropy, you obtain the same result, but of course with larger error bars, because you have dropped all the lensing information. You can also then say, okay, but I will also use the SLACS galaxies to learn about the mass density profile of elliptical galaxies. And in that case, you improve the precision, but it just so happens that you shift also the central value to something that is more consistent with Planck. So now this poses an interesting question. Is this telling us that the two samples of galaxies are not identical, SLACS and TD Cosmo, and therefore we cannot combine them? Is it a statistical fluctuation? Simply when you add data, you can fluctuate by 1 sigma or so. Or is this telling us that our previous assumption was not correct? And so at this stage, we are sort of rebuilding this from the foundations up. And unfortunately, there is a way forward. And the way forward is to obtain spatially resolved kinematics. So velocity dispersion and line of sight streaming motions of both the lensing galaxies and the lensing galaxies we use for time delay measurements, and external galaxies that are not time delay lenses. And so in a paper that Simon Birrer and I just published, we show that with the current sample of 7 time delay lenses and some AO-based or JWST-based integral field spectroscopy, you can get down to 2.5% precision, or 2.6% precision in this case, pretty simply. And if you have a larger sample, something that we are currently collecting, you can get back down to 1%. And so this is the target precision that we want to achieve, but this paper shows that this can be achieved without any assumption on the mass density profile. So
Tommaso, can I ask?
Yes, yeah, of course.
Yeah.
Who
so
is
can
this?
you
Sorry.
Can I ask? So can you describe, in more detail, how this breaks the degeneracies?
Yeah. So to first approximation, what is important is the radial dependency of the mass profile. And so if you make an assumption, if you decide that you don't want to use the lensing information because of the mass sheet degeneracy, you can use the traditional method, which is that what people have been doing in the local universe, for example, to study the mass density profile of elliptical galaxies for a long time, get spatially resolved kinematics. So getting the velocity dispersion and the line of sight velocity as a function of radius in 2D. And we've known that from local universe studies that you can then take that information and from that reconstruct sort of the radial dependency of the mass distribution in 3D with some degeneracies, of course, related to the anisotropy. And those can be mitigated by obtaining high quality kinematic data. They're not infinitely precise, and that's why you don't get to 0% error. You're limited to a certain amount of precision. Does this make sense?
Well, so if you let like the mass profile be completely free, right? So if you model it, let's say non-parametrically in 3D, does this break all degeneracies?
Well, of course, you have to have makes, yes. So if you make everything infinitely free, then you have no information. I think it's always a balance between you have to make reasonable assumptions when you try to model some data. And I think that's why the job of a physicist or astronomer is hard, right? Because you have to make assumptions that are reasonable and that are, allow for models that are complex enough to describe your data, but not flexible enough to describe your data, but not too flexible so that you can extract some of the information. And I think this is the balance that we, like everyone else, have to strike. And so certainly we will use, we use models that are informed by our understanding of how galaxies work. And we don't use, pixelated mass distributions. Yes.
Okay. Yeah. Okay. Yeah. Go ahead.
Sorry, Neil. I don't know. Were you done, Neil?
Yeah. Sure. Yeah.
I mean, can I actually kind of ask the reverse of that question? That I mean, your original analysis, what was so unreasonable about the profiles that you were using?
There was nothing unreasonable, I think. I think it was a pretty reasonable choice. It's just that it leads you to a conclusion that is quite strong. That is, you have to throw away lambda CDM. So I think it's reasonable to decide to try to see if you can get to the same result or a different one, dropping the assumption.
That's not, I don't think that's the correct way to do this. I mean, the question is there something wrong with your assumption? And your assumptions were motivated by simulations for NFW profiles, for example, and presumably simulations are not perfect because of baryonic effect and so on. So there is some wiggle room in the correct profile, but that can be included. You can, but that doesn't mean that the profiles are completely free. You do have.
I agree with you. I think I agree with you. I think this is like, so the second path is the extreme in the other direction. I think, and for example, in this paper that I showed you here, what we're doing here is we're using Navarro, Freck, and White models, but we allow for contraction or expansion as a response to baryonic processes. So I think the truth of I think the truth is probably somewhere in between, right? So probably you can imagine that power laws or NFW plus stars are a little too inflexible. And then you can imagine that the version where we exploit the full mass and mass shift degeneracy are too flexible. And so I think the truth will be somewhere in between. And so this kind of, to me, this sort of like this decision tree kind of like bookends where the precision will be somewhere between 2% and 8%.
Okay, fair enough, thanks.
And if someone had, I think if someone had very, very good simulations that are accurate to the sort of 100 parsec scale that we need to resolve here, we could certainly use those. I think that the problem is the simulations of massive ellipticals are difficult for a number of reasons. And so, I'm reluctant to say we just based our analysis on those.
Right.
Okay,
Like,
so now, yeah.
but given that we don't know how to predict galaxy structure, for these galaxies on these scales, aren't you concerned then, that making these assumptions might be overly restricting, the range of behaviors allowed in these models?
In what case? In which one of these cases?
Well, so if we knew, if we knew how to predict, how galaxies form,
Yes.
then I
Problem
agree
solved.
that we could, do this, right? But the problem, here, I guess, the concern, I guess, that people will have, is that, by making these parametric models that only have certain types of freedom in their anisotropy profiles, in their mass profiles, right? The concern is that we might be getting overly small error bars this way.
Yeah, no, I think it's a point well taken, and I certainly think that galaxies are not random collections of dark matter and gas. So galaxies, especially elliptical galaxies, are very regular objects. And so I think there's good reasons to try to describe them in a simplified way. So I've never seen a galaxy that is made of pixels of mass, right? Galaxies are made of things that are in some sort of dynamical equilibrium. And so I think it's justified to try to find some descriptions of them in terms of, you can think, cosmologically inspired or observationally inspired, regular parameterized form. The challenge is to find the ones that are correct. So you can give up and say, okay, I think I know nothing about galaxies, but I don't think that's the case. I think we know a lot about galaxies. And the challenge is just to quantify our knowledge about galaxies in a way that it's a fair representation of our knowledge, so that then you end up with the right error bars.
Okay, good. I'm going to interrupt here and ask Tommaso to move on.
Okay, thanks.
We'll run out of time.
Thanks, Mike. So yeah, okay. So
we can continue it in the questions at the end if there's more time.
Thank you. All right, so let's switch to the second topic now. So I think I've excited you on the first one in one way or another. Let's talk about the second topic then. What's the dark matter? So this is, if you ask a theorist, they have a lot of ideas of what dark matter could possibly be. And one of the things I'm not a theorist, but one of the things I sometimes do is I put myself in the shoes of a dark matter being and think, if I were a dark matter being and I would try to imagine the luminous world, what would it be like? And I would say, well, it would probably be like this, something like a proton, an electron, and a photon. And I couldn't be more wrong, because there's 3 quarks and leptons, and also 6 quarks, leptons, and all sorts of things. And so I think this is maybe true also for the dark sector. And it could be that the right answer is there's just one stable, massive particle that makes up all the dark matter, or it could be that it's a much more complicated space. And so what we would like to do is map this sort of like theory space into something we can observe, something like this. And again, this is not easy, because there's in between, there's growth of structure, there's formation of stars, processes that are intrinsically complicated and not perfectly understood. And so again, we can use lensing to learn about it. And this requires angular resolution sensitivities, as I will show you in a second. I'll show this again, and I won't show it again. And let's focus on satellites as a probe of the nature of dark matter. So this is 2 examples of 2 cosmological simulations of the same object, one carried out in cold dark matter, the one to the left, and you can see all these little structures that we call subhalos, and one to the right carried out in warm dark matter, where as due to free streaming of the warm dark matter particle, you can see that there's a deficit of low mass structure and subhalos in this picture. Now, if we had the ability to see directly dark matter, if we had ability to take pictures like this of the sky, we can easily tell which one of the 2 is the right one. The problem is that in the real world, when we observe something like this, something like the Milky Way or another galaxy, we can only see the subhalos that are forming stars. And these subhalos that are forming stars will, so if we don't see the subhalos, which we call satellites, it may be that they don't exist, or it may be that they're just not forming stars. And this is illustrated here. So if you have cold dark matter versus warm dark matter, the mass function, the number of subhalos as a function of mass in cold dark matter is almost a perfect power law, something that goes as m⁻². While in warm dark matter, you can expect that below some mass, which is related to the free streaming length or the free streaming mass, you have a deficit, and eventually this turns over. So being able to count these subhalos can tell you which one of the two models is a better representation of reality. Now, if you try to do this by counting satellites, which is something we and many others have done, the problem is that you can do the luminosity function of these satellites, but then when you try to compare it with numerical simulations, here there are some numerical simulations in CDM, LU and Illustris, and two semi-analytic models, one in CDM and one in warm dark matter. And you can see that the differences between the theoretical predictions are equally large if you change the implementation of baryonic physics than if you change the underlying dark matter physics. So when you try to observe only the luminous satellites, you're always subject to this degeneracy, that when you want to convert the number counts of luminous satellites into number counts of underlying subhalos, you really rely on your understanding of star formation at the small scales, which is a difficult and unsolved problem. So with lensing, you can do it directly. You can count the missing satellites because the derivatives of the gravitational potential are sensitive to the structure of mass on very small scales. In particular, the second derivatives can be sensitive to what happens on scales of milliarc seconds. And those are the scales that you need to resolve if you want to detect subhalos that are of order, say 10⁷ solar masses in virial mass. And so by using accurate measurements of the derivative of the gravitational potential, which we can infer from lensing observables, we can somehow constrain statistically the distribution of mass of these very small scales, which in turn tells us about the fundamental nature of dark matter. So this is an illustration, a movie done by my former student, Daniel Gilman, who is now at Toronto, in case you want to chat with him. So this is a zoom in on one of the multiple images, and there's a little satellite of 10⁸ solar masses. And you can see as the little satellite gets close to the image, the total flux coming from the image changes significantly. And the variation in the magnification, which is the flux of this image, can be quite substantial. So the presence of a single satellite can double easily the flux that you see if it's located in the right position. Now, naturally, in general, we are not in a situation where we just have one subhalo. The simulation I showed earlier showed that there's subhalos everywhere. There's subhalos in the plane of the lens, and there's subhalos along the line of sight. But as a proof of concept, we showed that this can be detected. This is a paper we wrote a few years ago, where we took a lens quasar with 4 images here, and we took some spectra with OSIRIS, that is an AO-assisted, adaptive optics-assisted integral field spectrograph, and we took spectra of each one of these quasar images. And in order to avoid microlensing, you want to look at narrow lines like O3, because these narrow lines come from a region that is large enough not to be microlensed by stars in the foreground galaxy, but small enough to be sensitive to the effects of subhalos of the order 10⁷, 10⁸ solar masses. And in this specific case, we did a very simple analysis where we said, okay, what happens if we try to put just one subhalo? And it turns out that your fit improves dramatically if you had one subhalo near image A, and this subhalo has to be around 10⁸ solar masses. And so this was proof of concept that shows that you've never seen this subhalo. You have no way to see it, first because it's very close to a bright quasar, and second, it may not have stars, but yet you can detect its presence through the gravitational lensing effect. Now, naturally, in reality, what you want to do is you want to simulate the entire line of sight of the universe and population of these subhalos. And this is what we've been doing in the last few years. This is a very computationally intensive problem that requires supercomputers because you have to carry out hundreds of thousands, if not millions of realizations of the light cone in order to compare with each simulations. And you have to also use semi-analytic models to tell you how the growth of structure will happen given a dark matter model. But the main result of this work so far, as we're limited ourselves to a simple warm dark matter case, is that based on 11 lenses, we've been able to obtain an upper limit on the mass of the dark matter particle, assuming there's just one. And this is for a thermal relic. So if the dark matter particle is a thermal relic, our data show that the mass has to be greater than 5 keV and 95% confidence level. Now, this is possibly the most stringent number regarding the free streaming length and the mass of the thermal relic, and it comes from just 11 lenses. And now we're in the process of extending this kind of analysis to a variety of dark matter models. So you can try to map any dark matter theory into observables. Say, for example, you can say, okay, what happens if you have a self-interacting dark matter model? In those cases, the densities of the halos will not be as high as they would be in a non-interacting dark matter model. And that gives you a little signature that you can detect with this kind of experiment. And there's other models that potentially leave signatures that you can detect with this kind of experiment. But in parallel to that, it's also important to extend the sample size. This was only based on 11 lenses, and you can imagine that the volume that you're probing is very small because it's light cones around each image. And so you want to increase the volume that you're sampling so that you're sensitive to this kind of like fluctuations in the small scale distribution of mass. And this plot here from Daniel Gilman shows that the precision that you achieve, in this case, given in terms of the mass of the thermal relic, depends on both the number of lenses you have, but also on the precision of the fluxes that you measure. And it's a difficult thing to measure the narrow lines of quasars because adaptive optics is limited in this fraction of sky that is accessible and in the wavelength ranges that are accessible. Hubble has relatively limited spectral resolution, so you cannot do this for most quasars. And what we really need to make progress here is to improve AO from the ground. But what would really be transformational is to use the James Webb Space Telescope, because at that point, you can use mid-infrared observations of the so-called dusty torus around AGN to do the same measurement. And that gives you additional advantages. You can try to infer also the size of these things. So that gives you not only access to more system, but also more precision per system. So we think this is just the beginning in terms of constraining the properties of dark matter. We think that there's lots of room for improvement, both on the theory side, to compute models and growth of structure and transform them into things that can be connected to lensing observables. But there's also a lot of progress that can come from future data. And so stay tuned. I think this will be very interesting in the next few years. So this concludes my presentation. So my summary is that this H0 tension, if confirmed, indicates a major departure from lambda CDM. So it's important to devote a lot of attention. And I think it's very important, given the stakes, to have multiple independent measurements. And one of those is gravitational time delays. So as you know, as I explained, so this is a powerful one-step method. And under reasonable assumption, we've reached 2%. Now we're restarting from scratch. And we see if we can achieve the same 2% precisions with much looser assumptions as time goes by. And the key there would be to obtain spatially resolved kinematics of these galaxies. And the second point is the nature of dark matter, which is unknown at the moment. And there are still a lot of alternatives to some cold dark matter that are viable. And I would like to test them and see if they are viable or if they can be rejected. And so far, we've been able to test some simple warm dark matter models and show that they don't seem to be required to set some upper limit, a lower limit on the mass of the dark matter particle. They're perfectly consistent with CDM. And if there is a dark matter particle, the mass has to be above 5 keV. But here, I think what is really exciting is many more stringent tests of broad classes of dark matter models are possible and will be carried out in the next few years. So thank you for listening, and I'm happy to take any more questions you might have.
Thank you.
Thank you.
I'm the only one with my sound on, but other people are clapping virtually.
Yes, I can see. Thank you, guys.
All right, thank you. Questions? Just call out is probably the easiest way.
Tommaso, can I ask a quick question? You also had masses on those plots with the, I mean, you had particle masses, but also halo masses. Is that the,
Where?
you just skipped over it, the next one, next slide. Yeah.
Vertical axis.
So is that the equivalent halo mass you would go down to in a CDM power spectrum?
No, that's called the half mode mass.
Mm-hmm.
So basically, you have to imagine that we parameterize the subhalo mass function as something with a turnover.
Mm-hmm.
And that's the location of the turnover. So where does it turn over with respect to CDM? And is
Okay.
it 10 to the 7 or 10 to the 9? Or 10 to the 8?
Okay. And is it dropping off? I guess how quickly is it dropping off? I mean, if I imagine something that was abruptly...
this is the right. It kind of goes like this.
Okay, and you're talking about the peak of the turnover there, exactly. Right? So the place where it would deviate by, let's say, a factor of 2 is going to be a couple of
higher,
higher than that. Yeah. Okay. Yeah, just checking. No, because those limits seem very low. I mean, I think an interesting model-independent question is, you know, what's the smallest structure we have any evidence for?
Yeah.
Right. And is that 10 to the 9? Is it 10 to the 9.5?
Oh, it's lower than that for sure.
Well, that's what I'm not clear about. Is it really lower if you're, I mean, as I say, if you had CDM just abruptly cutting off, where would it have to cut off?
Yeah, so you would be interested in seeing a model where this, instead of being a gentle turnover like this, is just a sharp cutoff.
Exactly.
Yeah, I think we can test that for sure. I mean, that's easy to implement.
Yeah.
And yeah, we can try it out and see what we get.
Mm-hmm.
My guess is it probably would be, as you say, significantly larger than the half mode mass. But I guess below 10 to the 9 because
below 10 to the 9.
Yeah,
okay. Okay, thanks.
Somewhere in the 10 to the 8s, you know, eyeballing it. Yeah.
Good. Thank you. Other questions?
Thank you.
I had one that's related to this. Maybe you said it and I missed it. I'm guessing in the case of the flux anomalies that most of these structures are not necessarily associated with the lens that's doing the strong lensing, but are just foreground and background random little blobs which happen to just be in the line of sight.
Yeah, it just so happens is one of those cases that is very unfortunate where the two contributions are comparable. And so you're not in a situation where you can neglect either one. And so the reason why it's taken us a long time to get to this point is that initially people were only modeling the plane of the lens, but it turns out that the contribution from the line of sight can be very important. And so what we do now is we model both. And so we do renderings of both. And so it takes a lot of computational power to do all this ray tracing and some tricks to be able to do it fast enough.
Thanks. Other questions? Don't be shy. I have one other one about the first part. It seems surprising to me that if I understood what you did, when you put in the constraint that the holy cow, etc. lenses with time delays had the same structure as SLAC lenses in the radial component, that actually changed H0 quite a bit, which implies that your previous fits, they were different from the SLAC lenses.
Yeah, so this is, okay, thank you for asking this question. I think it's important to highlight that. So it seems like it's changed quite a bit because you compare this to this.
Yeah.
But the thing is that you have to compare this to this, right? Under these assumptions here, you have to really compare this to this. And so from the point of view of the statistical errors in this one and in this one, this is only, a 1 sigma change. So the part that is confusing is that once you go down this branch, your uncertainties blow up. And these two measurements are statistically consistent with each other. It's just that the uncertainties have blown up. And so a shift in 1 sigma becomes quite important for the hypotension. And now it could be that as we get more data, we figure out that these galaxies are different. It's possible that SLACs are ellipticals at 0.2 and TD Cosmos are ellipticals at 0.5. So there could be a little bit of evolution in the mass profiles of ellipticals in that time range. We certainly know, for example, that ellipticals at higher redshift had smaller radii than at lower redshift. So there could be some form of evolution there. So that's certainly a possibility, but we just don't have the data now to tell which one of these options is the one that is correct.
But that branch means that you're still using the lensing data, or did you say that you'd thrown away all the lensing data?
So the only, so when you do the mass sheet transformation, the mass sheet transformation changes the mass profile, leaving invariant the images. So there's no information from the images on the mass profile. The only information that you're using on the mass profile comes from the stellar kinematics.
Okay. Right. Good. Any other questions? If there are no other questions, let's thank Tommaso again.
Thanks very much, Tommaso. Very nice talk.
Very
Really
nice
cool
to see
stuff.
you.
Good to
It's
see
been a
you.
while. Good to see
Yeah.
you.
Sometime we'll get to all again
Hopefully.
in person.
Yes, it would be great.